In 1984, astronaut Paul Scully Power became the first oceanographer in space. His interests, of course, were the oceans and how they appeared from an altitude of 300 kilometers. His observations and those made by satellites have given marine scientists the opportunity to study ocean processes over large areas at one time. Off the coast of western North America, these oceanographers are preparing for a dive to an unexplored region at the bottom of the Pacific Ocean. Here, they'll descend over 2,000 meters into the unfamiliar environment of the deep ocean basin. They're searching for submarine hot springs and undersea volcanoes, evidence for instability within the Earth's crust. Their view from the bottom of the sea is of our planet's last frontier of human exploration, the inner space of the ocean world. From the depths of the oceans to the heights of outer space, oceanographers, geophysicists, and marine geologists are beginning to appreciate just how complex the oceans really are. We too will investigate the oceans and learn how the Earth's biosphere, atmosphere, and lithosphere interact together to create this remarkable system. We'll also see how the health of our ocean environment is highly dependent on the activities of humans. What influences the unique chemistry of the seas? What forces have completely changed the shapes of oceans through time? And what actually drives the intricate movements of water as waves, tides, and currents? We'll answer these questions as we explore the fascinating world of physical oceanography. The oceans are vastly enormous, covering nearly 3/4 of the Earth's surface with water. This blanket of water, or hydrosphere, surrounds the continents as if they were islands in one continuous global ocean. Still, we subdivide the Earth's oceans and give each area distinct names. The 4 major oceans are the Indian, the Atlantic, Pacific, and Arctic oceans. All oceans can be thought of as having 3 main characteristics. The first being the chemistry of seawater. Second, the shape and topography of the ocean basins. And third, the movement of water within these basins. Let's look at each of these in more detail. The molecules of water that fill the oceans are constantly moving among the hydrosphere, atmosphere, and lithosphere interfaces in a process called the hydrologic cycle. They evaporate from the surface into the atmosphere. They condense as clouds and fall as rain or snow. And they run off the land, carrying with it dissolved salts or ions that make their way back to the oceans. It's these ions that give seawater its characteristically salty taste. Scientists call this property salinity. It averages about 35 parts per thousand, or the equivalent of dissolving 3.5 grams of salt into a liter of pure water. Seawater consists of water and the elements chlorine, sodium, magnesium, sulfur, and minute amounts of virtually all naturally occurring elements. Ocean water also contains dissolved gases that are constantly being absorbed or released at the ocean-atmosphere interface. Oxygen, for example, is given off by countless marine plants, and carbon dioxide is absorbed into the oceans by a host of biological and chemical processes. Scientists now fear this delicate balance is being disrupted by pollution, particularly by the human-made release of carbon dioxide and other so-called greenhouse gases that threaten to warm Earth's atmosphere. Some scientists think the excess carbon dioxide will be taken up by the oceans. Others are not so sure. If the oceans can't absorb this excess carbon dioxide, how might this affect Earth's climate? The second major feature of oceans are the landforms that lie hidden beneath their waters. The seafloor is an interface largely unexplored by humans, yet their features are revealed through indirect measurements such as sonar and echo sounding. If we could drain the seas and directly observe the floors of the ocean basins, we'd discover some of the most varied topography on Earth. The hills and valleys of the oceanic crust would seem like an intricate and convoluted container. All oceans are underlain by three major topographic areas: the ocean basin, the continental slope, and the continental shelf. Let's take a closer look at each. A continental shelf is a gently sloping platform that is part of the submerged edge of a continent. Although its width varies, the water depth is relatively shallow, usually less than 200 meters. Its surface is draped with thick layers of sediment that have been washed off the continents by rivers. In certain places, oil rigs on large platforms drill into these buried layers, tapping large reserves of oil and natural gas. Yet the production of fossil fuels can at times pose threats to the ocean environment. When this oil tanker ran aground in Alaska's Prince William Sound, 42 million liters of crude oil gushed into the ocean waters, polluting over 2,000 kilometers of coastline. Some of the oil evaporated, some settled to the bottom, and some washed up along the coast by the action of waves and tides. Despite the massive cleanup efforts, marine biologists predict this region will take tens, if not hundreds of years to recover to its natural state. The sunlit waters of the continental shelves host some of the world's most diverse ecosystems. Although these waters make up only 10% of the total ocean area, 90% of all ocean life is concentrated here. What biological processes account for such vast amounts of life? At the edge of the shelf, the seafloor plunges down a steeper surface called the continental slope. Oceanographers wonder how rugged canyons like these could have eroded into the continental slope in water hundreds of meters deep. Sweeping away from the base of the continental shelf, the ocean basin forms the central region of all oceans. The wide, flat-bottomed portion is called the abyssal plain, situated at an average depth of 3,000 meters. The ocean abyss is eternally dark because sunlight can only penetrate through the uppermost 100 meters of water. In the deepest places, the crushing weight of the water presses on objects 1,000 times greater than at sea level. At these depths, human exploration is possible only with the aid of submersibles such as the Alvin. These remarkable vehicles are capable of diving thousands of meters to the floor of the abyssal plain. Elsewhere, especially along the central areas of ocean basins, colossal mountain ranges rise sharply above the surrounding plains. They're called mid-ocean ridges and form chains of mountains that encircle the Earth for 74,000 kilometers. In effect, the largest topographic features on Earth. Near ridges or along the margins of island chains, submarine volcanoes called seamounts dot the ocean floor. Near the edges of some continents, other features called oceanic trenches form deep fractures in the Earth's crust. What accounts for these spectacular features? When marine geologists first interpreted data from the ocean floor, an astounding pattern emerged. The pattern they discovered was caused by the interaction of separate but interlocking crustal plates. Over long periods of time, these plates move slowly and actually change the shape of ocean basins. Where they collide, one plate may sink beneath the other along deep faults or trenches. Above the descending plate, the crust melts and rises along fractures to form chains of volcanoes or island arcs. This Pacific island arc lies next to the deepest place on Earth, the Mariana Trench. It lies 11,000 meters below the ocean surface, a trench deep enough to fit Mount Everest with 2,000 meters of water still above its peak. Volcanic activity also occurs where plates are separating. Here, new molten crust is pushed upward to form the mid-ocean ridges. This process is known as seafloor spreading. These are the sites of submarine hot springs or black smokers that erupt mineral-rich fluids from deep within the Earth's crust. Over hundreds of millions of years, the combined effect of all these processes causes the oceanic crust to expand and contract, and thus dramatically changes the shapes of oceans through time. The third and final feature we'll look at are the dynamic patterns of ocean movement. Movement within the oceans begins with the sun's radiant energy. As solar radiation filters through the atmosphere and strikes the Earth's surface, uneven heating creates winds in the atmosphere. These winds, in turn, sweep across the ocean surface, creating movement as waves. Waves are produced at the ocean-atmosphere interface, where winds shear the topmost layer of water. Here, water is pushed into regular shapes that rise and fall as storms pass over the ocean surface. More persistent and longer-lived patterns of wind create a different type of movement. These are surface currents, large-scale streams of wind-blown water that move within the top layers of the ocean. When combined with the influence of the Earth's rotation, surface currents follow circular patterns. Clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. What do surface currents look like? Satellite images reveal they are enormously complex features. The Gulf Stream, for example, is a well-known current that meanders and coils through the open sea like a river on land. Yet it carries a volume of water 100 times greater than the combined flow of all the rivers on Earth. Here, the warmest waters are shown in orange, the coolest in blue. The Gulf Stream pumps enough tropical water from the Caribbean Sea to warm the British Isles in the extreme North Atlantic Ocean. Can you think of other places where ocean currents affect the climate? Movement in the ocean also takes place deep below the surface waters. It works like this. Like the air above it, the sea surface is also unevenly heated by the sun's radiant energy. In this satellite time-lapse image of sea surface temperature, you can clearly see the warmer waters in red near the equator, the cooler waters near the poles. This uneven heating causes warm, tropical water to flow along the surface to polar regions. Here, water is cooled, becomes more dense, and then sinks toward the bottom. This type of oceanic convection is often called a density current. Where deep ocean currents rise along continental slopes, cold bottom waters bring nutrients to the surface in a process called an upwelling. Is it any wonder that the world's richest fishing grounds are located at upwelling sites? The sun is not the only extraterrestrial influence on our planet's oceans. The moon also has a role to play. As the moon revolves around the Earth, its gravitational tug pulls the oceans away from the crust. The Earth rotates beneath this bulge, creating tides, the periodic rise and fall of sea level. Millions of people who live along seacoasts are very much aware of the regularity of tides. They depend on its scheduled rise and fall to know when to navigate their boats, or else they may find themselves stranded embarrassingly far from shore.
The knowledge in oceanography, for some years
Thanks to the observations of oceanographers like Paul Scully Power and marine geologists aboard the Alvin, we now have a more global perspective of Earth's oceans. Satellite images give us dynamic views of sea surface temperatures, while improved techniques in sonar help us visualize the topography of the sea floor and add to our knowledge of Earth's restless crust. But with this new knowledge also comes a responsibility to take care of our oceans. After all, they're linked with the air we breathe and with the food we eat. They moderate our climate and make Earth a uniquely suitable place for life.